This is Juno 6 AS2 Physics 2 question 3, and it's a question on interference and superposition. The air in a tube closed at one end is excited to resonance. This is achieved using a small loudspeaker connected to an audio signal generator of variable frequency. The arrangement is shown as figure 3.1. The frequency of the generator, so there's the generator there and there's the loudspeaker. The frequency of the generator is adjusted until resonance is obtained. On figure 3.1, sketch a pattern representing the standing waves in the tube when the second resonant mode is obtained. Mark the positions of nodes and antinodes with the letters N and A respectively. Okay, so we'll just scan in a wee bit. So what you have there is, you know that you have only a quarter of a wavelength whenever you're in the first mode of vibration, and then the second mode of vibration you always have an antinode at the end. So the second mode of vibration, then you're going to get one complete closed loop, say about there. So there's your complete closed loop, and then open at the end, or your antinode at the end. And there's your antinode at the end again. So that's your second mode of vibration. And you're asked then to also mark the positions of the nodes, and the antinodes are in the middle, node and antinode in the middle with N and A. Describe how you would judge by ear the resonant frequency and how you would obtain as accurate a value as possible. So there's two wee bits to that question. The first bit, the resonant frequency is judged when you hear a maximum amplitude. And in other words, the loudest sound. So that's how you judge by ear. Then how would you obtain as accurate a value as possible? So what you'd have to do is adjust the frequency until loudest sound is heard. And then of course you're doing that by ear, so you have to repeat it. You must repeat it again and check, are you right? So repeat. And very often what they say then is to go up past the frequency you think it is and come back down again. And you might find that that's definitely the frequency that you think. Go above F and back down again. To check. Part C of the question. It is possible to use a small microphone connected to a cathode ray oscilloscope to confirm the resonant frequency judged by ear. The microphone is placed close to the mouth of the tube. The time base and Y sensitivity settings are adjusted until a clear trace is obtained. The frequency of the signal generator is again adjusted until resonance is obtained. Describe how observation of one feature of the cathode ray oscilloscope trace may be used to confirm that resonance is obtained. So how do we know resonance is obtained? And we know that it's obtained because you get a maximum amplitude or largest amplitude on your cathode ray oscilloscope. So that whole trace there, for example, would get much bigger, and that's your resonant position. When the resonant frequency is confirmed, the cathode ray oscilloscope trace is shown on figure 0.3. The horizontal length of the trace is 11.25 centimetres, and the time base setting on the cathode ray oscilloscope is 500 microseconds for every centimetre. Calculate the resonant frequency. Now if you have a wee look at that and count how many wavelengths you have in that 11.25 centimetres, you've got 1, 2 and a half. So you know that 2.5 time periods, because there's 2.5 waves there, is equal to 11.25 centimetres. Now that's not obviously a time, because you have to convert your 11.25 centimetres into a time using this scale. And the scale is that for every centimetre is worth 500 microseconds. So if you have 11.25 centimetres, you've got 11.25 times 500 microseconds in total. So we now know 2.5 time periods is 11.25 by 500 microseconds. So 1 time period is equal to 11.25 by 500 and micros by 10 to the minus 6. And it's divided by 2.5. And that gives you an answer of 2.25 by 10 to the minus 3 seconds. But we have to get frequency, and therefore frequency, if you remember, frequency is 1 over t, and 1 over this value here, so it's 1 over 2.25 by 10 to the minus 3. Just put that in a bracket so that you're not getting it mixed up. And therefore the answer comes out as 444 hertz. Okay, so I'll just go over that again. If I looked at this and maybe did it a different way, you can see there that you have 2.5 wavelengths. And if I have 11.5, it's 11.25 centimetres, and I know that I've got 2.5 wavelengths in there, then one wavelength is going to be, if I divide 11.25 divided by 2.5, it's going to be 4.5. So wavelength's worth 4.5 centimetres. Now that doesn't mean that that's a wavelength, that's actually a time period, because this is a time scale. The x-axis is always a time scale. So that 4.5 centimetres, if you then multiply it by the number of microseconds in a centimetre, that gives you the same answer, 2250 microseconds is your time period.